Hello, everyone. Welcome to this week's One World Combinatorics on Words seminar. Our speaker today is James Currie from the University of Winnipeg, and he is going to speak to us about analogs of overlap-freeness.
So my thanks to the organizers. Last week, 2 weeks ago, when Professor Espinosa spoke about dynamical systems and the rigidity of hierarchical systems, that's somewhat related to what's happening today. I'm going to look at three famous words, assuming my computer allows me to scroll. Yes, there we go. So to a Morse word is a fixed point of the morphism mapping 0 to 0, 1, 1 to 0, 1 to 1, 0. The period doubling word is another small morphism. 0 goes to 0, 1, but instead of 1 going to 1, 0, it goes to 0, 0. And of course, everyone's favorite, the Fibonacci word, a third small binary morphism where 0 maps to 0, 1, and 1 maps to 0. Now, I guess it's a bit of a toss-up which of these words has had the most ink, either the to a Morse word or the Fibonacci word. I like to study patterns. So, of course, a factor in a word is a well-known notion. Here we see that adoration contains ratio as a factor. For a pattern, word W contains pattern P if the image of P under a non-erasing morphism shows up in the word. So, for example, illegible encounters X, Y, X. So here, X maps to LE, Y maps to GIB, and then we have another LE. So illegible encounters the pattern XYX. Now, the to a Morse morphism is strongly related to overlap-freeness. Now, there are many ways to characterize overlaps and overlap-freeness. I'm going to do it in a slightly eccentric way, just on a whim. A word W is, a binary word W is overlap-free if it doesn't contain 0, 0, 0, or 1, 1, 1 as a factor, and it doesn't encounter the pattern XY, XY, X. So if you've never thought of this characterization before, normally, well, there's many ways to talk about words having overlaps. If a word has a cube, either it's a cube where the period is 1, and I've listed the two possibilities on top, or you have a period which is at least 2, in which case you will also contain XY, XY, X. And when we study overlap-free binary words, the to a morphism mu always shows up. A binary word is overlap-free if and only if mu of that word is overlap-free. If W is a finite overlap-free binary word, then we can parse W using mu. So W looks like X, mu of Y, Z, where Y is an overlap-free binary word, and X and Y, that should say X and Z, not X and Y. X and Z have lengths less than or equal to 2. And if U is an infinite binary overlap-free word, and in this talk, all of my infinite words are one-way infinite words. So in other words, maps from the positive integers, say, to the alphabet. So if U is a one-way infinite binary overlap-free word, then U looks like X, followed by mu of W, where W is overlap-free and X is either empty or a single letter. So we have these structure theorems for overlap-free words relating them to the to a Morse morphism. And this structure theorem is sort of an engine. Many results are known for overlap-free words. The structure theorems help you to prove these things. So for example, the number of binary overlap-free words of length n grows like n to the sigma. and sigma can be very finely specified. For example, sigma is between 1.3005 and 1.3098. The best results are from Younger's, Protasov-Blundell. Although I would say, for me, I always think of this as Cassain's result, because he used the structure theorem to give a specification in terms of regular languages of overlap-free words. The lexigraphically greatest infinite overlap-free word, starting with 0, is the two-way Morse sequence. And here I should mention that Alouche and Shalit and myself have a paper. If you want the lexigraphically least overlap-free words starting with any specified prefix, we can tell you how to do that. And again, this uses the structure theorem relating overlap-free words and the two-way Morse morphism. Fife's theorem gives a characterization of all the infinite overlap-free binary words. And as a bit of a side note, the only patterns encountered by the two-way Morse sequence, which are not factors of the two-way Morse sequence, are 00100 and its complement. And this result is due to Schur. So here's all sorts of things that are known for the two-way Morse morphism. So we think, oh, well, known for overlap-free words. So we think overlap-free words are very special. However, there are similar results for other morphisms, and that's what I'm going to talk about today. So to begin with, let's say that a binary word W is phi good if W does not contain 1 as a factor, and word W does not contain a factor which is almost a 4th power. So here, W does not contain a factor x, 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 x minus, where x minus is obtained from x by deleting just the last letter. So such a word I call phi good. So for example, this word 01001010 is phi good. We can see there's no 11 in there. And if I had a cube even, the period, this is length 8, so the period would be 1 or 2. So I quickly checked there's not even any cubes, so certainly it does not contain a factor x, 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 x minus. This word, however, has slipped up. There is a 1 as a factor, so that is not phi good. And this word, 01001010, that's not phi good, because if you take off the last letter, we've got x cubed, or x to the 4th rather. We've got 010101, and then we have 01 missing the last letter. So that contains x, 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 x minus. So there's this notion. So this notion looks a bit like being overlap-free. Now, when we study these phi good words, the Fibonacci morphism always shows up. The finite version is a little bit ugly. So I'm just going to say, if I have a finite binary word, which is, a binary word W is phi good, if and only if the image of W under phi is phi good, hence the name phi good. And when I look at an infinite phi good word, then it looks like the image under phi of a phi good word. And I have only added on a single letter, or nothing. So this is quite analogous to what's going on to two-way Morse. I have a class of binary words which avoid factors and a pattern and a factor. And under those conditions, the words have a structure theorem. They're actually, they come up by iterating the Fibonacci morphism. And you can prove similar results to what you prove for overlap-free words. So let's look at the lexigraphically least phi good word. So I will let L be the lexigraphically least infinite phi good word. I will let M be the lexigraphically greatest infinite phi good word. Now, it's not immediately obvious that there is a lexigraphically least phi good word. So there's a few lemmas there to show that these things exist if it's not clear. So we'll skip those existence theorems for now. And we'll jump right to characterizing the relationship between these words. So L is phi of M, and M is 1 phi of L. So how would we prove this? Well, I'll show that L looks like phi of M. Now, the Fibonacci word is phi good, and it has final segments which begin with 0, 0. So there are infinite phi good words beginning with 0, 0. So the lexigraphically least infinite phi good word has to begin with 0, 0. Now, when we look at the structure theorem, the last theorem on this page, says that if you have an infinite phi good word, it looks like the image of an infinite phi good word where either you put nothing in front of it or 1. So with L begins with 0, 0. So I put nothing in front of it. So L looks like phi of some phi good word. However, the map phi, remember the Fibonacci morphism, 0 maps to 0, 1, 1 maps to 0. It's order reversing on infinite words. So it follows that U must be lexigraphically maximal. Now, once we have this theorem, we can simply compose these results with themselves, and we get a relation on L. L is 0 phi squared L, and M is 1 phi squared M. So this allows us to calculate arbitrarily long prefixes of L and M. So for example, L begins with 0. So it begins with 0 of phi squared of 0, which is 0, 0, 1, 0. And therefore it begins with 0 phi squared of 0, 0, 1, 0. And we can get longer and longer prefixes of L. It would be nice if L turned out to be the Fibonacci word, but actually, and this corollary, I'm not saying it's obvious, but it's true. Every factor of the Fibonacci word is a factor of L, but there are infinitely many factors of L which are not factors of the Fibonacci word. In fact, L is not the fixed point of a binary morphism. And from the larger point of view, just that when we have a theorem that the set of phi good words has a structure theorem, we get this kind of lexigraphically least word. Like that is all you need to do these sorts of proofs. Let's look at a different variation. Delta. So here delta is the map. It's the morphism associated with the period doubling word. So the image of 0 is 0, 1. In this talk, the image of 0 is always 0, 1. But the image of 1 is 0, 0. So I'm going to say that a binary word W is delta good if word delta does not contain 1, 1 or 1, 0, 0, 1. And it doesn't encounter the patterns X, 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 X or X, 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 Y, X, Y, X, X. I will mention that those are actually the images under delta of 1, 1 and 1, 0, 0, 1, replacing zeros with X and ones with Y. So these two specifications are closely related. So I say that a binary word is delta good if it doesn't contain these factors and it doesn't encounter these patterns. So here's an example of a delta good word. We can see there's no 1, 1. There's no 1, 0, 0, 1. And again, with the fourth powers or the cubes, the length is 8. So the period of a cube would be 1 or 2. Well, there's 0, 0, 0. I guess there's a cube, but it doesn't extend to 0 to the 4th, and the word's not long enough for that to be extended. So here's an example of a delta good word. Here's one that isn't delta good: 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1. This encounters the pattern x, 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 y, x, y, x, x. Here's a word which is not delta good because it has 1, 0, 0, 1 at the end. So we have this notion of delta good words. It resembles the notion of overlap-free words. We forbid certain factors and we forbid some patterns. And this set of words has the same relationship to delta that the overlap-free words have to the two-way Morse morphism. When we study delta good words, the period doubling morphism delta always shows up. If U is a finite binary word, then U is delta good if and only if the image of U under delta is delta good. If W is delta good, finite delta good word, we can write it as A delta UB, where A is empty or a single letter, and B is empty or 0. And U has to be delta good. And if the length of W is at least 4, this factorization is unique. So in two-way Morse, in the case of overlap-free words in the two-way Morse morphism, we also have a uniqueness condition on factorizations of long enough words, which allows you to do enumeration. So we could take this and use it to do enumeration of these delta good words. If I have an infinite delta good word, it's the image of an infinite delta good word where we've simply tacked on a single letter at most at the beginning. So once again, we have these structure theorems. We could prove something about lexicographically least words, but instead, let's look at some of the other typical two-way Morse theorems. Let's look at Fife's theorem. Suppose W is an infinite delta good word. So by the previous structure theorem, we tack on a 0 or 1 possibly to a word which is the image under delta of an infinite delta good word. So remember that delta maps 0 to 1 to 0, 1, and it maps 1 to 0, 0. So W belongs to this language. I'm lying. That shouldn't be a star. It should be an omega. My apologies. So let's write W as a prefix, and then 0, 1 to some power, and then U1, such that the 0, 1 is not a factor of the prefix, and N1 is as large as possible. Of course, W cannot consist simply of zeros. It can't consist simply of 1s, because then we would have a 4th power. And X, 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 that pattern is not encountered by a delta good word. So eventually, we see a 0, 1. So we find the first appearance of 0, 1, and it could be 0, 1, 0, 1 squared, 0, 1 cubed, but we can't have 0, 1 to the 4th. So N1 has to be 1, 2, or 3, and after that, things start with the block 0, 0. That means that 0, 1, U1 starts with, well, it starts with 0, 1, 0, 0, which is the image of 0, 1 under delta. And this delta of 0, 1 is not a factor of Y2, where Y2 is Y1, 0, 1 to the N1 minus 1. So let's write W equals Y2 delta of 0, 1 to the N2, U2. And where N2 is as large as possible. So N, it says N0, pardon my slide, should be N2 is 1, 2, or 3. And U2 starts with delta of 0, 0. And we iterate, we continue to parse off maximal blocks delta to the Ni of 0, 1 near the beginning of W. These are analogous to Morse blocks in overlap-free words. Now let's look at the other direction. Oh, not quite yet. So we get a sequence of finite words of the form prefix delta to the n of 0, 1, where n is maximal, and delta to the n of 0, 1 doesn't appear in y. So this is like parsing Morse blocks from an infinite overlap-free word. Looking at this in a different direction, suppose I start with a finite word w, which has a suffix delta to the n of 0, 1, where n is greater than or equal to 0, and n is as large as possible. And I'll write w looks like y delta to the n of 0, 1. We define mappings alpha, beta, gamma on w by, we keep the y for alpha, and then we follow by delta to the n plus 1 of 0, 1. For beta, we keep the y, and we extend by delta to the n plus 1 of 0, 0, 1. And gamma, we keep the y and extend by delta to the n plus 1 of 0, 0, 1. So each of these has w as a prefix and a suffix delta to the n plus 1 of 0, 1. So here's an example. I start with this word w. I pull off the highest power of delta to the n from the end of it. So it ends in 0, 1, but actually it ends in delta squared of 0, 1. Here, this is the image of 0, the image of 1. So this is the image of 0, 1, which is the image of 0. So this is delta squared of 0, and this is delta squared of 1. So I've got this prefix y, and I've got, it's followed by delta squared of 0, 1. So in this case, alpha of w, I keep the y, and now I have delta cubed of 0 followed by delta cubed of 1. For beta, I keep the y. I have delta cubed of 0, 0, 1. And for gamma, I have y followed by delta cubed of 0, 0, 0, 1. So suppose u is a word over alpha, beta, and gamma. It looks like u1, u2 up to un. Then I define 0, 1 bullet u. First, I'll apply u1 to 0, 1. Then I'll apply u2 to 0, 1, and so on. So we have composition in the reverse order. First, u1 is applied to 0, 1, then u2 is applied to u1 of 0, 1, and so on. So for an infinite sequence, bold u over alpha, beta, gamma, we define 0, 1 bullet u to be the binary sequence having each 0, 1 bullet u1 up to un as a prefix. So this takes a finite word and it generates from it an infinite word. And if we go back a couple of slides, if I have any infinite delta good word, then it's actually created by a sequence of alphas, betas, and gammas, because n1 has to be 0, 1, or 2, n2 has to be 0, 1, or 2, and so on. So any infinite delta good word is created using a sequence of alphas, betas, and gammas. The remaining question is, if I have an infinite sequence of alphas and betas and gammas, does it create a delta good word? So here's an example of how these operations work. If I have 0, 1 bullet alpha, beta, gamma, this means 0, 1 bullet alpha, and then we apply beta, gamma. And for alpha, 0, 1 starts with the empty word followed by delta 0 of 0, 1. So it's replaced by the empty word followed by delta 1 of 0, 1. Now I apply beta. So here's something starting with the empty word followed by delta 1 of 0, 1. So that gets replaced by delta squared of 0, 0, 1. That's the application of beta. And then we apply gamma. Now here, this looks like delta squared of 0 followed by delta squared of 0, 1. So gamma operates on this delta squared of 0, 1 and replaces it by delta cubed of 0, 0, 0, 1. And we grow words. So this is Fife's theorem for delta good words. The infinite delta good words, starting with 0, 1, are precisely the words 0, 1, bullet U, where U can be walked on this automaton. So if you've read Nerad's thesis, or Burstell's characterization of Fife's theorem, then this result will seem familiar. If you want to have an infinite overlap-free word, it is created in much the same way. We start with a finite word, we bullet it with an infinite string of alpha, betas, and gammas, and we produce an infinite word. And then an automaton characterizes exactly which sequences of alphas, betas, and gammas gives us the overlap-free words, in this case here, the delta good words. And what does the proof look like? Well, the proof uses the structure theorem, and this proof is mimicking, sorry, wrong direction. This proof is mimicking Nerad's proof of Fife's theorem. So let G be the set of one-sided infinite delta good words. I'll use a subscript U if G has a prefix U. So G sub U is the set of infinite delta good words which start with U. So we begin with a lemma. Delta of W is good if and only if W is good. 1 followed by delta of W is good if and only if 0 of W is good. And 0 delta of W is good, and this is more complicated. That happens if and only if 1 W is good, or W is a good word starting with 0, 0, 1. So this lemma is proved from the structure theorem, and part C, it has mild complications. Now, G is a set of delta good words. W is a set of words over alpha, beta, and gamma, such that 0, 1 bullet F is good. So W is the set of infinite strings of alpha, beta, and gamma, which when you apply them to 0, 1, you get an infinite good word. So here's part 1 of the ingredients of proving Fife's theorem. Next, we have this result. If I have a finite word U and F is an infinite word, both of them over alpha, beta, and gamma, let 0, 1 dot F be X. Then if I apply UF to 0, 1, what happens? Well, U has length K, and I start with 0, 1. When I apply the first letter of U to it, that gives me delta of 0, 1. Then I apply the second letter of U to that, and that gives me delta squared of 0, 1. And when I've applied all K letters of U, I end up with a delta to the K of 0, 1 as a suffix of 0, 1 delta U. And that suffix of U is the highest power of U, excuse me, it's the highest power of delta, which is a suffix of 0, 1 bullet U. So this is at the end of 0, 1 bullet U. And then F is going to be applied to that. F will take this highest power and start doing things to it. But we're actually starting with delta to the K of 0, 1. So one ends up with this identity. So using this identity and the previous lemma, we can start to show that we can start to show, for example, this, according to this automaton, if I take gamma and I apply it to a word, I should get to the same place as if I apply gamma gamma, because there's a loop here. Or if I take beta and apply it to a word, that should be the same as applying beta alpha alpha. So in other words, there are, when I look at W and I look at cosets of W, I should have some identities. So getting the automaton in our theorem means proving identities such as a beta gamma inverse of W is equal to gamma inverse of W. So this means the set of words which I take a sequence W and I strip off an initial beta and gamma. So in other words, I have a sequence which produces a good word and I strip off beta and gamma. That's the same as the sequences of good words with a gamma stripped off. So I need this in order to collapse the states of my automaton. Originally, you could begin with not a finite automaton, but with an infinite automaton where the states correspond to every single infinite string over alpha, beta, and gamma. But I identify the states of this automaton to end up with the finite automaton that I've shown. So for example, if you look at beta gamma f, that belongs to W, if and only if 0, 1 with beta gamma f applied to it is good. However, 0, 1 with beta gamma of f applied to it, beta gamma has length 2, so that looks like 0, 1 bullet beta gamma. We strip off the delta squared 0, 1 from the end of that, and then we apply delta squared of x to that. And so here is beta gamma of 0, 1. I strip this off the end. Oh, sorry, this whole thing is beta gamma. I strip off delta squared from the end. Then I apply delta squared of x to it. I recognize this is delta of 0, 0, 1, 0, 1, which is, I parse this to get this. So this must be good. However, now I use my lemma, delta of something is good if and only if the argument is good. But now I have 0 delta of something is good. That happens if and only if 1, so 0 delta W is good if and only if 1 W is good, or W belongs to G0001. If I flip back, I'm using these relations. So 0 delta W is good if and only if 1 W is good, or W belongs to G001. So eventually, beta gamma is in W if and only if 00x is good. But we calculate similarly, gamma f is in W if and only if 00x is good. So that means that beta gamma and gamma get you to the same place in the automaton. So beta gamma goes up and down, and gamma just goes down. So they get you to the same place in the automaton. So you perform a number of these calculations, and you find that various states of the automaton are equal, and we end up with the indicated finite automaton. So Fife's theorem is not really about overlap-free words. It's about words that have a structure theorem and a morphism. Being able to characterize the lexicographically least word avoiding certain factors and patterns. Well, if you choose the correct set of words that you're avoiding, you get a structure theorem, and you can do the lexicographically least things. So all of these things, which are quite interesting for 2A Morse, enumeration, here's the lexicographically least overlap-free word, here's a characterization of the infinite overlap-free words. We can do the same things for sets of words which are related to the Fibonacci morphism, sets of words which are related to the period doubling morphism. So there's a larger phenomenon going on. Now, looking at the period doubling word, this is not exactly related in the same way to the structure theorem, although you always need to use the structure theorem when you're dealing with these delta good words. But at the beginning, I mentioned Schur's theorem. The only patterns in 2A Morse, which are not factors of 2A Morse, are 0, 0, 1, 0, 0, and its complement. Now, the period doubling word, full disclosure, the period doubling word is closely related to the 2A Morse word. And you can derive it from the 2A Morse word by some simple operations, which is why I wanted to show that you can do tricks with the Fibonacci morphism also, because otherwise you could say, well, period doubling morphism, 2A Morse, it's the same thing. Of course you have a Fife's theorem. Of course you can characterize the lexicographically least word. So that's why I'm also looking at the Fibonacci morphism. And anyway, you have a very nice characterization of the patterns, the binary patterns, which appear in 2A Morse. However, when we look at D, the period doubling word, it's much more complicated. It's actually infinitely more complicated. Now, any factor starting with 0 of the period doubling word can be parsed using the Fibonacci morphism. Because, well, I won't try to improvise a proof of the lemma. However, any factor of the period doubling word that starts with 0 can be parsed using the Fibonacci morphism, and any factor that ends in 0 can be factored with the reverse of the Fibonacci morphism. So that means that the word D has an inverse image under phi and under phi reverse. I should say factors of D. And so here's the theorem. Word P is a binary pattern encountered by the period doubling word if and only if one of the following holds. One of P and the complement of P is a factor of D, or of phi inverse of D, or of the inverse image of D under this reverse morphism. One of P and the complement of P is among this list of 10 patterns, and those two possibilities are distinct. So the first category, this contains infinitely many patterns. I can take any factor of D and apply any factor of D appears as a pattern, but also if I take the inverse image of a factor of D under one of these morphisms, that appears also. And the inverse image under D, excuse me, the inverse image here gives me a word which is not in D in general. So it's quite messy. So and the proof is a long. It's searching down a tree until the tree dies. So anyway, I thought this sort of followed up on Espinosa's talk a bit, because he was talking about the rigidity of hierarchical systems. And that's exactly what we're seeing here, because if I have these overlap-free words, well, they're rigid in that there is a structure theorem. There really is only one way to get them. You're always iterating the same morphism. The same is true for these phi-good words. They always show up. They're always parsable using the Fibonacci morphism. And the same is true for these delta good words. They're always showing up as parsed by the period doubling morphism. So I should have a slide that says thank you, but I'll just say thank you verbally. And
thanks, James. Does anyone have any questions? Hajime.
So thank you for your nice talk. So you consider delta good word, and if you consider another substitution, then we can consider analogy. So what kind of property is important for the proof of your theorem? What kind of property of delta is important to prove your theory?
yes, I think that, I mean, the big conjecture would be that if you take any morphism and you can sort of force the morphism by forbidding certain factors and forbidding certain patterns. So I'm looking at very small binary morphisms because they're small enough to analyze. So it would be interesting to look at other famous morphisms. There's a sort of a there is a menagerie of morphisms that we know. So it would be interesting to look at the various small morphisms and see what happens. I mean, obviously, you want a morphism which is growing. Well, I guess if it's not growing, it's pretty easy to do things because you only have finitely many things to look at. But yes, I think this should just generalize all over the place. I have to say that if we go back to the definition of phi good words, that's a pretty simple definition. Now, for historical reasons, we're interested in overlap-free words, but this is a pretty simple class of words. I'm not claiming that it's inherently interesting on its own, but the connection to the Fibonacci words makes it interesting. Similarly, when we look at the delta good words, that's also a fairly simple definition. It's a little bit more complicated here. And actually, while I was doing this, there are some different definitions you could use. You know, there are different sets of forbidden factors and so on. I thought this was about as elegant as I could make it. Maybe someone else could come up with a better way to force the morphism.
Thank you.
Thank you.
Jeff, do you have a question?
Yeah, I was wondering if the classes of infinite words that you study here all have polynomial growth, or like to a more like overlap-free does. The others do too, or?
I believe they would have. Overlap-free. Excuse me, polynomial growth, because of the sort of structure theorem. I think that would sort of immediately sort of imply. I mean, you iterate the morphism, you've got finite variation. So I think that would give you low growth.
So you're only going to be able to do this for classes where you have this polynomial growth. But
yes,
but you and Narad had some kind of structure theorem where it was like n to the log n.
Yes, we studied words x, x, x reverse, and x, x reverse x, and they both have both of those. So binary words avoiding x, x followed by the reverse of x, that has growth. Words avoiding that pattern, binary words, has growth between polynomial and exponential. And similarly, and with an easier proof, if you look at binary words avoiding x, x reverse x, that has growth which is between polynomial and exponential. But I mean, for me, somehow the morphisms, these are classical morphisms, the Fibonacci morphism, the period doubling morphism. So the class of words is sort of, I mean, it's interesting because of the morphism, not the other way around. So I'm not starting with classes of words. I'm sort of cheating, and I'm starting with morphisms. I'm trying to force the morphisms. And I think that many proofs For example, recently, when we worked on binary rich words, you end up with a similar structure theorem. And often you end up, in cases where there's been successful enumerations, you often end up with structure theorems of this sort. But as you say, only polynomial growth.
Are there any other questions? If not, yeah, thanks a lot, James.